Thank you. Good morning, everyone. I'm Andronick. I'm the CEO of both Proofcraft and the seL4 Foundation. It's a great pleasure to be here and be part of this seminar, so thank you very much for the invitation. What I'd like to share today is that common goal, common mission that a lot of people in this room and in the world have, which is to make formally verified software becoming the standard, the default, at least when it comes to deploy it in critical systems, safety critical systems, security critical systems, for instance, that can be subject to cyber attacks. So focusing here on the software side of things and software that is deployed in critical systems. What I'd like to start with is the state of the art. That's the state of the art. This could be interpreted in many ways, so I'd like to really be explicit of what I mean here. What I mean here is that the state of the art can be understood differently from different people. The perception of what the state of the art is today in the quality of software is somehow wrong. So what I'd like to claim here is that formally verified software is today the state of the art, not tomorrow. And I'll try to build on that during my presentation. So if I had to summarize in one slide, what I'd like to say is 4 main points about formal verified software. Firstly, that it's feasible for real software that can be deployed. That it does work, it does protect against cyber attacks, for instance. It can scale to large systems to some extent, and I'll explain a few areas of how can this be achieved. And it can be more and more accessible by non-experts, and I'll explain that as well. And this is why I'm saying that today it is starting to be the state of the art, and we should try to work together to establish that. When I say can scale as a third point, it mainly means the standard way of scaling in terms of code sizes. The fourth point about being accessible can be also understood as a scalability problem, as Brad Martins here would mention when he was establishing the previous program, is saying it scales in the number of people. So the number of people that can either develop formal methods or develop products with formal method, or actually just deploy a system that has formally verified systems inside. So more and more people developing or just using formally verified artifacts. Stepping back a little bit, why I'm going there, in 1969 we had the seminal paper from Tony Hall, where he described the program verification and the fact that, in theory, you can derive all the properties of your program by purely deductive reasoning, looking at the program source code. He did say that this is going to take some effort, right? It's going to have a cost. But it did say that eventually the practical advantages of program proving should outweigh the difficulty. Why? Because the cost of programming error would be much larger than the cost of having done the program verification in the first place. Now, 40 years later, Tony did a retrospective paper where he discussed what went differently from what he thought, and specifically on that cost problem. He said that things happened slightly differently than what he envisioned. And this is mainly because when the issue ever came to court, the defense of the state-of-the-art practice would prevail. Formal verification was not the state-of-the-art. People had applied the state-of-the-art, and bugs still happened, but they had done their best. So that's where I want to say that the state-of-the-art now, today, is becoming formal verification. So that's where the state-of-the-art theme is coming into. I'll use throughout this presentation the example of seL4, which is where I have the experience and background. seL4 is this formally verified microkernel. But I'd like you to take it as one example. Thankfully, we have now a number of other big and successful projects in the area of formally verified software. And I'd really like all of these projects to think about how they can make a case for these 4 points to keep pushing the fact that, yes, now we can do that at a large scale. So I'll go through those 3 points one by one, 4 points, The fact that, yes, formal verification is feasible, as seL4 is a low-level microkernel that has been formally verified. I'll come back to it. It does protect against cyber attacks. It's scaled in code sizes, and I'll use the idea that isolation can be used as a leverage to reach larger code bases. I'll explain how. And finally, how we are working to reduce the reliance on formal method experts. So before we go there, I just want to mention one more thing, which is in 2011, a few years after the first big seL4 proofs happened, and it had quite a bit of impact, both in the formal method community and the systems community. Well, it meant that we had a number of journalists wanting to contact us and make press articles about it. And one of them interviewed or asked for an email interview from Tony Hall, and I have some of those comments. Unfortunately, they didn't make it in the article. So the only thing I have is an email, so either you trust me or you can just take those quotes as mine if you want. But one that I really like is that when total absence of error is a requirement, meaning when we're actually talking about safety and security critical system, then failure to verify, to apply formal verification, will and should be treated legally as negligence, as in other areas of engineering, right? This can only happen when we have established that this is a state of the art. And this is more than 10 years ago. So a lot of progress has happened since then in providing tools and tool support and framework to be able to do that in a more mundane fashion. And yeah, he was mentioning that the seL4 microkernel was one sort of demonstration that convinced us that this is possible. And again, since then, a lot of other very exciting projects happen in that area. So this is why I want to take seL4 as an example. But again, please try to think about how that can apply to other systems. So first of all, formally verified operating system kernel. Yes, it is feasible to apply formal verification to a low-level program. What is seL4 in one sentence? It's a high assurance, high performance operating system microkernel. Let's unpack that. It's an operating system microkernel. What it means is that it runs at the core of any software systems. It is the most critical part of your system. It does the abstraction. But the more important thing, its job is to isolate what's critical and what's not critical on top. So in terms of application. So if there is a malicious attack or some bugs that can happen on the untrusted part, the job of seL4 is to make sure that the critical part is protected, and that if anything is compromised on the untrusted part, then it cannot propagate to the critical part. So that's the job of a kernel, and that's what seL4 does. If you think about some concrete example that we'll see later on in actual projects, in a car, the critical part can be the brakes, the uncritical part, the entertainment system. As we've seen in car hacking, you wouldn't ask someone to hack your entertainment system and through that access to your brake. Same thing with drones or quadcopters. You could have the critical part being the communication with the ground station, telling the drone where it should fly to, and then you could have a camera feed that is untrusted and could potentially be hacked. So these are just a couple of examples. Now moving on to the second part, which is the high performance. High performance is important for two reasons. One, because it's a microkernel, so it controls all the accesses, and therefore it is the bottleneck. So if the performance is bad, the performance of your entire system is bad. The second aspect is why performance is important for your entire system, because otherwise it's not used, right? Otherwise, formal methods are just on toy system or algorithm and things like that. So you want the two together so that it's actually being deployed. And finally, the most important thing, the high assurance. Big stack, you don't have to understand. These are all proofs and specifications and models. What they mean is that we have a mathematical proof, so the highest level of assurance, that seL4 is correct. It does exactly what the specification does. And you have a formal proof that it enforces isolation. So you have a proven assertion that the non-critical part cannot propagate to the critical part. So, yeah, formal verification to something that is low-level, complex, and can be embedded on system. And this, if I just represent that whole thing as a small radar, has been done not just once, but it has been done on a number of different architectures, number of different configurations, because it's being used, and then customer says, well, I want it on something else. And this is mainly what Proofcraft as a company is doing. I've created the company with 2 co-founders about 3 years ago, and this is providing commercial support to develop formally verified software, and in particular for seL4. And yet another data point, this is a cold graph of seL4. It is highly complex, highly non-modular, because it is a microkernel. Everything that can be modular is at the application level. So just different ways of saying, yes, it is something very complex, very low level, but formal verification has been able to be applied to it. Was it a big deal? Well, we've received a number of awards for it. The Hall of Fame award in particular, that's from the systems community. And one of the statements has the state-of-the-art mention in it. This is on the performance side, because that's what systems people really care about. But they basically said, you know, they can actually do formal verification on something that has the state-of-the-art performance. So slowly getting into the minds that this can happen today. And a year ago, we also had the Software System Award for, again, the seL4 verification with things like industrial strengths, high performance, so things that are happening for real systems. So this is, in a nutshell, what I wanted to say to show that as an example with seL4, formal verified software today is feasible for complex systems. Does it work? Does it actually add assurance about the security or the safety of your system? So I'm going to talk about how, in the case of seL4, we were able to show that it protects against cyber attacks. For that, I'll come back to the HACMS program funded by JAPA between 2012 and 2018. That was led by Collins with Darren Coffer here in the room that is going to be on the panel this afternoon. And we had a number of partners there. And the seL4 technology was used, but not only. Like, we have a number of other technologies that were used to push formal verification inside a number of systems. Again, the reason I use that example, although it's a couple of years old, is because it also received an award, like the Game Changer Award. And it mentions enabling high assurance, so meaning formally verified software, in a number of real systems, like helicopters, quadcopters, ground vehicles, and so on. So what happened in that program? Well, in all of those systems, you were able to run something like you were able to run seL4 and separate what was trusted from untrusted. And we also had a professional team of hackers, a red team, whose job was to show that the security was enforced. So we just had a question in a previous talk about how do you measure that? Well, the way it was done in that program is that we were asking the red team to make an assessment before we were adding any formal verification, any formal artifacts, and they could get control over everything. And then we transitioned to a system where we applied all of our formal verification methods, and in particular running on top of the verified seL4 microkernel. And we even gave the red team root access to the non-critical part. And it ran on a real helicopter, so that's Boeing Unmanned Little Bird. And the red team could get control of the camera and everything, so the camera went off, but they would not be able to send commands to the vehicle to be able to fly it anywhere, all right? So that was one example where we could show with a previous and after demonstration that using formal verification has an impact and can protect against cyber attacks. DARPA is not the only one that has been funding, in particular seL4, which is, again, where I have experience with. We have a number of organizations that has been funding this technology along the years. So the AORD, Asian Office of US Air Force, US Army, DHS, more recently the UK's National Cybersecurity Centre, and also private companies like Hensoldt Cyber, Excalibytes, and so on. Another data point, seL4 is an open source product. it has an open source foundation, and it has a number of members. And what's interesting here is that we have a mix of academic members, industry, and government organization. And all of them supporting the fact that seL4 in particular, but formally verified technology is something that should be supported because it does have an impact on real products. So that's what I wanted to say for the second aspect with that example in mind. Now, about scalability, right? So seL4 is about 10,000 lines of code. When we did that formal verification for the first time, that was huge. Applying formal verification to 10,000 lines of code, it's huge. Obviously, like normal software systems these days are much, much larger. But I just want to say that I just want to mention one angle, which is how you use isolation to allow that scalability. So if you think about a system like that, that is not necessarily the way I've already architected it like this, but you just think about it as a huge software stack. I'll just mention the approach that we are pushing forward with the seL4 methodology, which is to componentize, isolate, and then verify. So first of all, you componentize your architecture, so that's quite standard. You analyze which components you have there. But then, most importantly, you defined through design, by construction, which one are trusted and untrusted. And by that I mean like what resources they have access to and who communicates with who, right? And this, by definition, defines what is trusted and what is untrusted. By design, you should try to minimize, as a general rule of minimize trusted computing base, you should minimize the amount of code that should be trusted, okay? But by construction, by definition, if you define something as untrusted, it means that the property, the behavior of that component, by construction, cannot violate your property of interest, right? So that's really important because then what you want is first building that on a trustworthy foundation, like a microkernel, to be able to enforce that. Because what we've done in the previous step is just defining who has access to what. How do you show that this is enforced? How do you make sure that the untrusted part cannot access, let's say, the memory of the trusted part, the cryptographic key or something, right? And this is exactly the job of the microkernel or a kernel, right? The kernel is there to enforce that if you don't have access to it, the access will be forbidden. This also controls all communications. So if two components communicate, they have to go through the kernel. So now the kernel is the most trusted or the most critical part of your system. And then you apply verification to these aspects. And this doesn't mean you're going to verify the entire system. I'll come back to it in the next slide. But really, the kernel has to be verified because it is the most critical part. If it crashes, there's nothing that you can do against that. But it's also the component that allows that isolation. Your critical part obviously needs to be verified as well because it has enough power, it has enough authority to violate any property because you have given it enough rights. Thankfully, this is something that we see a lot of progress in the community here, right? In verifying user-level application code. And this can have several layers depending, like, you can have, like, if it's highly critical, you can have very strong formal verification story there, or you can start with, static analyzer, or you can already do memory safety. You can have several layers of assurance there. And this is where there's still work to do as a community to make sure that we can combine those technologies. But this is what happened at the critical part. And then on the architecture, what you need to prove is that you have set up your access correctly. That's the only thing you need to do. Because the main point I want to say here is once you've done those three jobs, you don't have to look into that box. Because you have shown by construction that it cannot violate the properties of interest. So that's one way of seeing isolation as a way to scale to a much larger system. You can have formal assurance of a given property on a very large code base without having to verify every single line of code of that code base. Only the trusted computing base. So that's what I meant to give one angle for that isolation as leverage. Just in terms of scalability, last week there was the seL4 Summit in Sydney, where I attended. A number of exciting talks there. One of them is seL4 being in cars today, on the road, in mass production. So yes, it can scale to actual real systems. Finally, in terms of scalability, in terms of people. So this is probably the most ongoing work that we have as a community, how we make sure that formal verification can be used more and more by non-experts. One thing that I want to mention first is that idea of cyber retrofit, which was coined in the HACCMS program again. And the idea was that on the team in HACCMS, we had Boeing engineers that were supposed to use, to transition their system to be using seL4. And we were not allowed to see any of their code. And so the engineers themselves, without any of our input, apart from questions, were able to do that transition. So there are two messages here. One is that it can be progressive, right? It's not like today, if you haven't done it, you can only apply it to your next product in 5 years. You can transition your existing system now to gradually be using formal verification artifacts. But the second message here is that the Boeing engineers were not formal method experts, and they did not develop formal methods during that project, but they did use a formally verified artifact and could benefit from it without having the expertise. And actually that terms of cyber retrofit has been used over and over. We've heard about it at the seL4 Summit last week by 4 or 5 different organizations. And even in the CASE program, which was a follow-up from HACCMS, the Collins team was also able to use formally verified artifact from engineers that are in a different department. So that's not necessarily scalability in terms of people doing formal verification, but actually using formal verification artifacts. In terms of using, scaling the formal verification to non-experts, this is one of the main goals of the Provers program that is just starting, again led by Darren here at Collins with a number of partners. And at Proofcraft in particular, our goal is to reduce the reliance on experts, so on us. So right now, if you go to the seL4 website and you want to use seL4, you have 32, 35 different configurations, different chips that you can use. But as of 2 years ago, there were only 2 or 3, one per architecture that had the tick being verified. And every time you wanted to use the one that just the next one, you had to ask us to do some work. What we want is to automate that completely. And even a bit from the start of Provers, we've already moved that to about 15 to 16 platforms. And eventually we want all platforms to be verified, but also new ones to be automatically verified by just having to check that your configuration has a number of specifications. So for instance, the number of domains or certain hardware configuration. As long as they satisfy some conditions, they should be verified. So this is, again, one way to reduce the reliance on experts. That concludes what I wanted to say here. Again, this is just giving an example with the seL4 kernel. I want to claim that we should push the fact that with all of the evidence that we have today, formally verified software is today what people should be using. There's still work to do, but as Robert was saying, we shouldn't wait the next 10 years to start using it, right? It is today the state of the art, and if people embed software in systems that can be life critical or mission critical, this is the state of the art they should be using. Thank you.